Now you are familiar with the calculation of vapor pressure of liquids using Raoult's law. Will the value obtained in such calculations match with the experimentally obtained vapor pressure of solutions? On this basis, we classify solutions into two types. In today's class, it is regarding these two types of solutions that we are going to discuss: ideal solutions and non-ideal solutions. First, let us consider ideal solutions. Ideal solutions are solutions that obey Raoult's law at all compositions. So what are ideal solutions? They obey Raoult's law at all concentrations. Now, they obey Raoult's law means the first condition for the solution to be ideal will be the partial pressure of one component, P1, should be equal to its mole fraction x1 into P01, vapor pressure of the pure component. Similarly, P2 will be equal to x2 P02. Second condition is that the components on mixing should neither liberate energy nor absorb. That means the mixing process should not be exothermic or endothermic. There should be no enthalpy change during the mixing process, or we say delta H mix equal to 0. Third property of ideal solution is that delta V mix equal to 0. That is, during mixing of the two components, there should be no change in the volume, or the volume of the solution will be equal to volume of the solute plus volume of the solvent. For example, if we mix 100 ml of A and 100 ml of B, we should get 200 ml of the solution. There should be no change in volume during the mixing process, or delta V mix equal to 0. What type of liquids will show this ideal property? In the beginning classes, we have seen intermolecular attraction plays an important role in the vapor pressure. Structurally similar compounds will have similar intermolecular attraction. In the solute A, the attractive force is between A and A. In the solvent B, attractive force is between B and B. When they mix, the new attractive force come to the picture, namely A and B. That is between solute molecule and the solvent molecule. If they are similar, the molecule will behave ideally. In fact, no solution is 100% ideal. Examples for solutions which are almost ideal are benzene plus toluene. Both are hydrocarbons of similar structure. Then we have N-heptane, that is normal heptane plus normal hexane mixture. Chloroethane, bromoethane will be another example for ideal solution. To sum up, what are the properties of ideal solutions? 1. They obey Raoult's law at all compositions. Secondly, delta H mix equal to 0. Third, delta V mix equal to 0. Fourth, AB attraction will be similar to AA attraction and BB attraction. The vapor pressure of the solution which behave ideally will be in between that of the components. The second type of solution is non-ideal solutions. Non-ideal solutions will not obey Raoult's law during the entire range of compositions. When we say they do not obey, the value obtained experimentally may be greater than or less than that calculated from the Raoult's law. Hence, there are two types of non-ideal solutions, one showing positive deviation, another showing negative deviation. What type of solutions will show positive deviations? The vapor pressure measured experimentally will be greater than that calculated from the Raoult's law. P1 will be greater than X1 P01 and P2 will be greater than X2 P02. This is the first property of solutions showing positive deviation. Second property is that when such liquids are mixed, heat will be absorbed, or the mixing process is endothermic in nature and delta H mix will be positive or greater than 0. Third property is that the volume of solution will be slightly greater than the volume of the solute plus solvent. That is, during the mixing process, there will be an increase in volume, or delta V mix will be greater than 0, or we say it is positive. What type of liquids will show positive deviation from Raoult's law? Again, intermolecular attraction comes to the picture. If the attraction between solute and the solvent, that is A and B, is less than the attraction between AA or BB, the solutions show positive deviation. When the intermolecular attraction decreases during the formation of the solution, more number of molecules of the solute and the solvent can go to the vapor phase. So, the experimental value of vapor pressure will be slightly greater than that obtained by using Raoult's law. One example to this category is the solution formed between water and ethanol. Water and ethanol are hydrogen bonded liquid. What type of compound will show hydrogen bonding? When hydrogen is attached to more electronegative atoms like oxygen, fluorine, nitrogen, etc., there will be a dipole-dipole force, and this bonding is called hydrogen bonding. Water is a hydrogen bonded liquid. Oxygen being more electronegative, that will carry a slight negative charge, and hydrogen will carry a slight positive charge, and molecules in water are held together by strong hydrogen bonding. In ethanol also, hydrogen bonding is present between the oxygen atom of one molecule and the hydrogen atom of the next molecule. So, when ethanol and water are mixed, some of the existing bonds between the molecules will be broken to form a new bonding between ethanol molecule and water molecule. And this bonding is weaker than the bonding in alcohol and water. So what will be the result of this? More number of water molecule and more number of alcohol molecule are free to go to the vapor phase now. Therefore, the observed vapor pressure will be slightly greater than the value calculated from Raoult's law. When 100 ml of ethanol is mixed with 100 ml of water, the resulting volume will be slightly greater than 200. Why there is an increase in volume? This is because the attraction between ethanol molecule and water molecule is weaker than that is present in water and ethanol. So, when the attraction decreases, molecules will move slightly away from one another. This leads to an increase in the volume of the solution. When ethanol is mixed with water, there will be a cooling effect. That is, temperature will come down. Why? Because when ethanol is added to water, some of the hydrogen bonds are broken. Bond breaking is an endothermic process, and the energy required is absorbed from the solution. This leads to decrease in temperature. Ethanol plus acetone is another example for solution showing positive deviation. Now let us see regarding solutions showing negative deviation. The first property of such a solution is that the vapor pressure observed experimentally will be slightly less than that calculated using Raoult's law. That is, P1 will be less than X1 P01 and P2 will be less than X2 P02. Second point is that delta H mix will be negative. That is, the enthalpy change is less than 0 or the process of mixing is exothermic in nature. That is, heat is liberated when the two liquid components are mixed together. Third property is delta V mix is less than 0. That is negative again. That is, volume decreases during mixing. For example, when you mix 100 ml of sulfuric acid and 100 ml of water, the resulting volume of the solution will be not 200 but 198. There is a decrease of 2 ml during process of mixing. That is, delta V will be equal to negative. What type of solutions will show negative deviation from Raoult's law? Here, the A-B attraction, that is attraction between the solute and the solvent, is greater than that is present in AA or BB. That is, the force of attraction increases during the mixing process. Increase in the mixing process will decrease the number of molecules that go to the vapor phase. That is why the vapor pressure is less than that is calculated from the Raoult's law. And we have seen in the case of positive deviation, attraction plays an important role in the volume of the liquid. Here, attraction increases during mixing. So the molecules are coming closer, hence there is a decrease in volume. The increased force of attraction is due to formation of new stronger bonds, and formation of bond is always exothermic in nature. so delta H is negative. One example to this category of solution is the solution obtained by mixing acetone and chloroform. There is no hydrogen bonding in acetone, there is no hydrogen bonding in chloroform. But when the two liquids are mixed, a strong hydrogen bond will be formed between the oxygen atom of acetone and the hydrogen atom of chloroform. Thus, attraction increases, number of molecules escaping to the vapor phase decreases, vapor pressure decreases, molecules come closer, so volume decreases, formation of the new hydrogen bond releases the energy and the process becomes exothermic. Hydrochloric acid plus water, sulfuric acid plus water, nitric acid plus water all lead to the formation of solutions showing negative deviation from Raoult's law. Now, there are two different types of solutions, ideal solutions and non-ideal solutions. During problem solving, first calculate the total vapor pressure of the solution using Raoult's law and compare the value with the experimentally obtained value. If both are equal, solution will be ideal. If they are not equal, solution will be non-ideal. If the experimentally obtained value is greater than that obtained from Raoult's law, then the solution shows positive deviation. If the experimentally obtained value is less than that is obtained from Raoult's law, the solution shows negative deviation. So this concept will be understood better when we solve a problem. Liquids A and B have vapor pressures of 280 mm and 168 mm of mercury respectively. The solution of these two with 0.32 mole fraction of A has a total vapor pressure of 276 mm of mercury. Predict the nature of the solution. The total pressure will be equal to XA P0A plus XB P0B. XA, the mole fraction is given as 0.32. Then XB will be 1 minus 0.32. P0A is given as 168 and P0B is given as 276. Substituting, we will be getting 0.32 into 280 plus 0.68 into 168 equal to 89.6 plus 114.24 equal to 203.84 millimeters of mercury. Now this is the vapor pressure of the solution calculated using Raoult's law. Now the total observed vapor pressure is equal to 276 millimeters of mercury. It is the value given in the problem. So what we can observe now is the observed pressure is greater than the pressure calculated, and therefore the solution show positive deviation from Raoult's law. It is a non-ideal solution and it shows positive deviation from Raoult's law. Now let us see what is meant by vapor pressure composition diagrams. It is a graph obtained by plotting vapor pressure of a liquid at different mole fractions. In the graph, the composition is taken on the x-axis and vapor pressure is taken on the y-axis. This point corresponds to x1 equal to 1. Along the x-axis, it decreases, and when it reaches the other end, x1 equal to 0. When x1 is 1, it means this pure component 1 and its vapor pressure correspond to P0 1. It can be marked along the y-axis at any point because the values are not given. So this point corresponds to P0, 1. When x1 is equal to 0, there will be no x1 present, so its vapor pressure will be equal to 0 at this point. When P0A is joined with this point, we get a line which represents the vapor pressure of the component 1. Similarly, now at this point, x2 is equal to 0. When x1 is equal to 1, automatically x2 will be 0. And along the x-axis, at the other end, x2 will be equal to 1. When x2 is equal to 1, this is the pure component 2, and the vapor pressure will correspond to P02 along the vapor pressure axis. This also you can have anywhere along the y-axis. Let it be here, and this value corresponds to P02. When x2 is equal to 0, there is no second component, so its vapor pressure will be 0. When these 2 points are joined, you get this line which represents the vapor pressure curve of component 2. When P01 and P02 points are joined, you get a line corresponding to the vapor pressure of the solution. Thus, this gives the vapor pressure composition diagram of an ideal solution. From this graph, you can calculate the vapor pressure corresponding to any mole fraction. Consider the point on the x-axis denoted by the letter A. We want to calculate the partial vapor pressures and vapor pressures of the liquid corresponding to the point A. Now draw a perpendicular from this point. It meets the vapor pressure curves at points B, C and D. Now AC will denote the vapor pressure of component 1. AB will denote the vapor pressure of component 2, and AD will represent the vapor pressure of the solution. In the case of solutions showing positive deviation and negative deviation, the curve will be slightly different from the ideal curve. First, let us see the vapor pressure composition diagram of a solution showing positive deviation. In the graph, the dotted lines indicate ideal behavior, and the graph corresponding to the vapor pressure of solution showing positive deviation will have a convex surface. The curve will be slightly going upward and ending in the required points. You can see all the things: vapor pressure of component 1, vapor pressure of component 2, as well as vapor pressure of the solution will be going upwards because it is the positive deviation. In the case of solution showing negative deviation, the vapor pressure is less than the calculated value, so it will be having a concave surface when compared to the vapor pressure composition diagram of ideal solution. I think you might have heard the term distillation. Distillation is a process of separating a liquid mixture into its components based on the difference in boiling point. Usually, when a liquid mixture is heated, the more volatile component, that is the component with higher vapor pressure, will easily escape to the vapor phase. Therefore, composition of the liquid mixture will be different in the liquid phase and the vapor phase. There are liquid mixtures which will not obey this particular pattern. They are called azeotropes. or azeotropic mixture. Now what is an azeotrope? Azeotropes are liquid mixtures which will have the same mole fraction in the liquid phase and in the vapor phase. So when an azeotrope is heated, the mixture will get converted into the vapor phase without any change in the composition of the mixture. They are also called as constant boiling mixtures. Azeotropes are formed only by non-ideal solutions. Ideal solutions will not form azeotropes. Since there are two types of non-ideal solutions, naturally there will be two types of azeotropes also. The first type is called minimum boiling azeotropes. They are also known as positive azeotropes because they are formed from solutions showing positive deviation. One example is that of ethyl alcohol having a composition 95% alcohol and 5% water. With this particular composition, the mixture will have a boiling point which is less than that of the component because their vapor pressure will be higher than expected. Ethanol boils at 78.3 degrees Celsius, water at 100 degrees Celsius, and this mixture of ethanol and water azeotrope will boil at a lower temperature 78.1 degree Celsius. Second type of azeotrope is the maximum boiling azeotropes. They are known as negative azeotropes and are formed from liquid solutions showing negative deviation from RAOULT'S law. One common example is nitric acid, which contains 68% nitric acid and remaining 32% is water. The boiling point of this mixture will be greater than the boiling point of nitric acid and water because they show negative deviation. When the deviation is negative, vapor pressure will be less and the boiling point will be more. The azeotropes cannot be separated into two pure components by simple fractional distillation. For alcohol, you have seen just now, it forms an azeotrope, 95% ethanol, 5% water. When this mixture is boiled, the vapor also will have the same composition. So by distillation, we cannot prepare 100% pure alcohol. For that, some other methods are available. So azeotropes are constant boiling mixtures which will be distilling without undergoing any change in the composition. So here we wind up the discussion on ideal and non-ideal solutions. In the next session, we will have a new topic on colligative properties.